So it is just, yeah, there's no difference.
So, as in, if it is given in a question, is that if it is lye, then we are assuming the crystal form, and caustic soda it would be in the solution.
I mean, so caustic soda is available as a solid flakes, so it is called as a. um so when you say lye, it is a some solution. I mean, so if I have to tell you that it's a solution, somebody would have to tell you the concentration also, right? So there are no general answers to your questions. What exactly are you trying to ask?
So there was a question that I was solving, in that I got confused because it was written that it was solid weight percent, but everything was in solution. So
Now, which question is that? And then can we see that
uh,
question? You can present your screen, or you can present from wherever you are seeing,
1 minute, sir.
because it's sort of difficult to give some generalized answer unless I see the question. So should I stop sharing?
Yes, sir. 1 minute.
Okay, I'll stop sharing so you can share. Meeting is being recorded. What about your afternoon lecture? Is it there?
Sir, I have not yet got a confirmation.
Okay. Till that time, other people can tell me if they have solved the ammonia problem. Are there any difficulties? Do we need to solve it here? Anybody has solved the ammonia problem, ammonia flow sheet problem?
Yes, sir.
Yes,
Yes,
sir.
sir.
Are
Yes,
there
sir.
Okay, good, good. Are there any difficulties? Do we need to solve?
So I'm showing the question.
Yeah. Actually, you're using your camera now. So if you're, can you share your screen rather than using camera? Because in the
Okay,
camera,
I'll do it. 1 minute.
1 second. Okay, it's not very clear. So ammonia problem, do we need to solve here, or can we go to the next problem? What is the general consensus?
So the next problem.
Next problem.
So please solve it in the class.
Solve. Okay. We will see the solution.
Yes.
Once we see, once we discuss Arya's, yeah, now Arya is sharing his screen. This is better because now we can see. I still can't see anything. In it, can you just read out? It's so difficult.
Yes, sir. I'll read it out.
Uh,
In a textile mill, a double effect water evaporator system concentrates weak liquor containing 4% by mass caustic soda to produce a lye containing 25% solids by mass. Calculate the evaporation of water per
So
100 kg
4%,
feed.
correct. So 4% means it is a solution only. 25% also is a solution. It is so
So
only so once you start going beyond 50-60%, then it becomes like a solid mass flakes. So
it said
4% is the
solid by
solution.
mass, that's why I got confused, I guess.
Okay, okay. 4% is solution. Okay, so are you able to see the screen now?
Yes, sir.
Yeah. So basis we wanted 1 ton of ammonia. So if we think in terms of kgs, it is 1000 kilograms. We are going to see the quick solution. We are not going to see everything. Okay, so we'll just try to see how to solve rather than looking at the complete solution. So now we are talking about reactions. So we better work in terms of moles. So if I say 1000 kilograms, then molecular weight is 17. So 1000 divided by 17, this will be how much? 58.82 kilomoles, right? Now, if you think of the reaction, your reaction is N2 plus 3H2 giving 2NH3. Based on this stoichiometry, now we can write kilomoles of both the things coming in to the reactor, nitrogen as well as hydrogen. So if it is 58.82 kilomoles of ammonia, that means we must have fed 29.41 kilomoles of nitrogen, and 3 times that number we must have fed 88.24 kilomoles of hydrogen. Everybody okay so far? Maybe I will put it in different color so that we are clear that we are doing this calculation. So we are just taking material balance, control volume across this reactor, and we have got the nitrogen and hydrogen coming into this reactor. Everybody okay so far?
Yes, sir.
If anybody has doubts, we can discuss. Now, if you think about where this nitrogen is coming from, this nitrogen, all of it is coming from the air. So if you think about it, if you are taking this blue as a control volume, right, whatever nitrogen is going out from here, from this stream going out of the control volume, there is no ammonia that has reacted either in the, there is no nitrogen that has reacted in the partial oxidation, in the shift converter, in the CO2 removal system. There is no nitrogen coming in to this control volume from the reformer. Okay. All the nitrogen that is coming in is coming from this air stream. So that means if I want 29.41 kilomoles of nitrogen going to the ammonia reactor, I must have fed 29.41 kilomoles of nitrogen from this air stream. And air containing 79 and 21 mole percent of nitrogen and oxygen. So the oxygen must be 29.41 multiplied by 21 divided by 79 kilomoles. That means oxygen fed automatically along with the nitrogen, because we are feeding air, must be 7.82 kilomoles. I'm just rounding off to 3 digits, 3 significant figures. Okay, now if you look at this control volume, the partial oxidation reactor as a control volume, our reaction is methane plus oxygen giving us carbon dioxide and water vapor. So now we need 2 of water vapor just to balance the hydrogen, and correspondingly 2 of oxygen to balance the carbon dioxide, and so balance the oxygen atoms. Okay, so if we are having 7.82 kilomoles of oxygen coming in, as per stoichiometry, if I am talking about this control volume, I must have left, I am coming from reformer, I must be having 7.82 divided by 2 moles, so that is 3.91 kilomoles of methane I must have fed. Do you agree with that?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Now CO2 is all coming from, there is no CO2 that is formed in the reformer. All the CO2 is formed only in the partial oxidation by combustion of methane with oxygen. So every kilomole of methane that we are feeding, 1 kilomole of carbon dioxide will come. So that means carbon dioxide must also be 3.91 kilomoles. Nitrogen is going to remain unreacted, that is going to be 29.41 kilomoles. Okay. Oxygen will all go away. Should we say that water here, should we say water here is 2 times 3.91? That means 7.82. Should we say that?
No.
No,
No,
sir.
Should we
sir.
say that water here is 7.82?
No,
So
sir.
some unreacted
sir.
water will also be there.
Correct. So obviously, if I think of, if I'm talking about the red control volume, water is generated by way of the reaction, but there is also water coming in along with this stream that is coming into the partial oxidation section. So water, I still cannot say anything. Carbon monoxide, I still can't say anything because I don't know how much is coming. Hydrogen, I still can't say anything because I don't know how much is coming, because hydrogen is not generated in this reaction. Okay. But we can go forward. So nitrogen coming into this water gas. Now if I take this water gas shift reaction as a control volume, 29.41 kilomoles are coming in, 29.41 kilomoles must be going out. Okay. If I look at the control volume across CO2 removal system, all the CO2 is gone, all the nitrogen will remain unaffected in the CO2 removal system, all the hydrogen will remain unaffected in the CO2 removal system. So I must be having 88.24 kilomoles of hydrogen coming out of the water gas shift reaction block and going into the CO2 removal system. Should I say that CO2 removal, CO2 coming out of the water gas removal is also 3.91?
No, sir.
No. Why not?
Sir, because the remaining CO2, that is 3.91 plus the shift reaction CO2 is coming out.
Correct. So now in the shift reactor, water and CO are going to react and they're going to generate CO2. Because I don't know anything about water and CO coming in, I cannot say anything about this CO2 as well. All right. Okay. Can we go backwards now? I don't know anything about the methane coming in. I don't know anything about the water coming in. Why? Because I have no idea about how much reforming reaction is taking place. I need to have some amount of methane left after the water, after the reforming, that I know, but I don't know how much water I require. I don't know how much CO will be generated corresponding to the reaction. Therefore, both these things are unknown. Now, can anybody tell me, besides the CR, can anybody tell me how do we get all the unknowns?
Sir,
Sir,
can I?
sir,
Sir, can I?
sir, can
Sir, can I?
Yeah, let us see who has not yet answered. Praveen, you have been answering for quite some time. Any other person wants
Okay,
to
sir.
answer?
Sir, can
sir,
I?
Yeah, sure. Smith.
Sir, consider the amount of CH4 reacted as X.
Amount of CH4 reacted as X.
Yes,
Okay.
sir.
Not coming in.
No.
Okay. So in this section, what you are saying is kilomoles. Rather than saying amount, we should be very specific. By
Yes, sir.
amount, do you mean kgs or grams or kilomoles or meter cube or what?
Kilomoles.
Kilomoles. So let us say, assume kilomoles of methane reacting in reformer is equal to X. Okay.
Yes, sir.
Okay.
According to that, we will balance the reaction.
Now tell me how you will balance the reaction.
So,
Our reaction is
X.
straightforward. CH4 plus H2O giving us CO plus 3 hydrogen. Okay. Now tell me.
Sir, so H2O will, number of moles of H2O will be also X.
Where? Reacted.
Yes, sir.
Okay. So amount of CH4 comma H2O reacted are is equal to X. Okay.
And CO generated will be also X, and
CO
H2,
generated is equal to X. H2
and
generated is equal to 3X. Okay.
yes, sir.
Now,
Uh, so total feed of a CH4 will be X plus 3.91.
okay. So CH4 fed to the reformer, if you are saying in terms of kilomoles, will be X plus 3.91. Okay, fine.
Sir,
If anybody disagrees, please stop and ask. Please unmute and ask. If anybody dislikes or disagrees with Smith solution,
sir,
please.
consider
Yeah.
excess of H2O, which is outlet of a reformer, as
Hmm.
Y.
In terms of kilomoles.
Yes, sir.
Okay, so you want this to be Y kilomoles. Okay.
And therefore the outlet of oxidation chamber will be Y plus 7.82.
Yes, so Y plus 7.82. Okay, so this would be Y plus 7.82. If anybody has not understood, you can ask and Smith can explain. Okay,
Sir,
Smith, go ahead.
now we will write the reaction for shift reaction.
Okay. Yeah, tell me. Shift
X
reaction
moles
is
of
already written here.
X kilomoles of CO reacts with X kilomoles of H2O
Huh.
to produce X kilomoles of H2 and X kilomoles of CO2.
Okay. So,
So X is equal to Y plus 7.82.
how did you get X is equal to Y plus 7.82?
Sir, because
What is your X? X is your amount of methane reacting in the reformer.
yes,
Now you
sir.
are using some other X.
No, sir, that only.
Now, how did you say that X is equal to Y plus 7.82?
Sir, because kilomoles of H2O reacted.
In what? Kilomoles
Sir,
of H2 reacted in the shift gas. Okay.
let me check.
Okay. We are just waiting for
Sir,
Smith. Yeah, Smith.
sir, the total H2 outlet of the shift reactor will be 4x.
Total H2 outlet of shift reactor is 4x. How did you get that?
Sir, because in the shift reaction, the amount of H2 generated will be X, and
No. In the shift reactor, how did you say that amount of X, amount of CO2, H2 generated will be X? How did you get that?
because by stoichiometry, sir, because
No,
X
you are
kilomoles of.
you are right, but we are missing something. You should also say that I should write X here. Is that what you're saying?
Sir, can you repeat?
Are you able to see the screen?
Yes, sir.
If
Sir,
are,
yes. Sir, I told CO
so
generated
you
is
told
equal to
only
X.
here, you told only based on stoichiometry, you have to tell me that you should write it in the table.
Yes, sir. Sorry, sir.
So no, no, no need to say sorry. All I'm saying is that it is for everybody to understand. People may not understand so very quickly while you are explaining. So, and then we should say hydrogen also is 3x.
Yes, sir.
So we should write this in the table. Only then we will be able to understand. So now the CO, there's no CO that is generated in the partial oxidation. There is no hydrogen that is reacted or generated in the partial oxidation. So this CO also will be X. This hydrogen also will be 3x. Is that what you're saying, Smith?
Yes, sir.
Okay. Now go ahead. Now, has everybody understood up to this so far?
Yes, sir.
Anybody has doubts? Smith is here to answer. I'm only showing Smith's solution.
Yes, sir.
Okay. Now Smith, go ahead.
Sir, so X kilomoles of CO reacted with X kilomole,
So now the
3x.
stoichiometry is 1:1. Therefore, water that is present and CO that is present, they will react with each other in
Yes,
the
sir.
1:1 stoichiometry. So you are saying X must be equal to Y plus 7.82 to make sure that the stoichiometry of CO and water is 1:1.
Yes, sir.
Okay. Now,
Sir, the amount produced of H2, kilomoles of H2 produced in the shift reaction is X.
correct. So hydrogen will be now 3x that is coming from the reforming plus x that is generated in the uh,
Yes, sir.
shift gas reaction. So this hydrogen coming out of the water gas shift reactor must be equal to 4x, and you
Yes,
already
sir.
know that 4x has to be equal to 88.24. So we have to say that 4x is 88.24. Therefore x is equal to 88.24 would be 22.06, right? If x is 22.06, correspondingly y would be 22.06 minus 7.82. 22.06 minus 7.82, that would be 14.24, right?
Yes, sir.
So this y must be 14.24, this x must be 22.06, this 3x must be 3 times that number, 66.18, this 3x must be 66.18, this x must be 22.06, this y plus 7.82 we already know that must be 22.06, CO2 must be 3.91. Okay, now this 4x is already there, 88.24. Yeah, okay, now go ahead. Smith, go ahead.
Sir, then the CO2 removed from the CO2 removal system will be 3.91 plus X.
Yeah, so 3.91 plus 22.06, 22.06, that means 25.97 must be here and 25.97 must be going out. Okay.
Yes, sir.
Okay, what else now?
Sir, then
So then we have got the x also. We have got x plus
yes,
3.91 is the methane that is fed. So x plus 3.91, so that is 22.06 plus 3.91, that is 25.97. Okay. And water,
X plus Y will be water.
right, 14.24. 14.24 is coming out of the reforming, and 22.06 has reacted. So that means this is 36.3. kilomoles. Right? Have we got everything? Have we got everything? Anybody agrees? Anybody disagrees? Anybody stuck somewhere? Anybody thinks that we are pulling out rabbits out of a hat?
No, sir. Agreed.
No? Okay.
Agreed to the solution.
Okay. Anybody else thinks that we are doing magic? If you want to know whether whatever Smith has done, whether it is right or wrong, you can always take this whole plant as a control volume. If you think about this whole plant as a control volume, you want to depict this whole plant. I have methane coming, that is 25.97 kilomoles. I have water coming, that is 36.3 kilomoles. I have air coming. I will just rub this out. I have air coming in, which means I have nitrogen and oxygen coming in, 29.41 and 7.82 kilomoles. Then I have CO2 that is going out from this CO2 removal system. It is going out of the plant. This is 25.97 kilomoles. And I have ammonia that is going out of the plant. This is 58.82 kilomoles. Right? Now, if you want to know whether your answers are right or wrong, you can do several balances across this plant. First of all, you can do total material balance. Multiply 25.97 by 16, you will get kgs of methane coming in. Same way, you can calculate kgs of water coming in. You can calculate kgs of air coming in. You can calculate kgs of CO2 going out. You can calculate kgs of ammonia going out. And then all the total material balance has to be satisfied. Total kgs coming in of methane plus water plus air must be equal to the total kgs of carbon dioxide going out and ammonia going out. Right? That is one kind of balance that you can think about, total material balance. All the kgs coming in must be equal to all the kgs going out, irrespective of what is happening in the plant. There's no nuclear reaction happening in the plant. So all the kgs coming in must be exactly equal to all the kgs going out. That is one. Second thing you can think about is the elemental balance. You can think about the carbon atoms coming in and carbon atoms going out. You can think about the oxygen atoms coming in. Oxygen atoms coming in must be equal to all the oxygen atoms going out as CO2. Sorry, I should not circle 25.97. All the oxygen atoms going out as carbon dioxide. All the hydrogen atoms coming in from methane, all the hydrogen atoms coming in from water must be equal to all the hydrogen atoms going out in the ammonia. All the nitrogen atoms coming in from air and all the nitrogen atoms going out in ammonia. So atomic balances also have to be satisfied. So that's one more way you can check whether your answers are right or wrong. If you have made some calculation mistake, you will be able to immediately spot it if you try doing overall material balances, overall atom balances. Because atoms are not going to be destroyed. They are going to appear either in reactants or as products. Atoms are not destructible unless we are talking about nuclear reactions. All right, everybody okay so far? Anybody has any doubts? Okay, so far?
Yes,
Any
sir.
issues?
Yes, sir. No, sir.
Yes, sir.
Yeah, go ahead, go ahead. Somebody was asking something. No, nobody was asking. Somebody was asking anything or not asking. Okay, shall we go ahead?
Yes, sir.
Yeah.
Yes, sir.
So one again very important feature, amount of kgs of CO2 generated per metric ton of ammonia. How much is this number? So this number, so we have taken basis as 1 metric ton. CO2 generated is 25.97 kilomoles. So 25.97 kilomoles into 44 molecular weight of carbon dioxide. This is 1142. 1142.68. So let's just say 1143 kgs. So do you realize that every time 1 metric ton of ammonia is produced, 1143 kgs of carbon dioxide are emitted into atmosphere. Where do we consume ammonia? Are you consuming ammonia in your day-to-day life?
Sir, fertilizer.
Fertilizers, right? Ammonia is used.
Sir,
Yeah,
polymers.
which polymer?
Um,
You're right, but which polymer?
Nylon.
Amide based fibers. But yeah, anyway, that market is small. If you think about the worldwide food
Epsilon
production,
caprolactam.
yeah, go ahead, go ahead. Yeah,
Epsilon caprolactam. So,
yeah, correct. So all the things, so those market is that market is small. The amount of ammonia going to nitric acid and going to fertilizers across the whole world
Cooling reagents. Cooling.
is very large. So majority of the ammonia is consumed to make fertilizers. So every time you use a fertilizer that has a nitrogen atom in it, you can be sure that it has come from 1 mole of ammonia, and every 1,000 kilograms of ammonia that is used, we are generating 1143 kilograms of carbon dioxide. So that is the CO2 footprint of all our fertilizers, right? It's a huge number. If you see the amount of fertilizers that are consumed in the country, so majority of the fertilizer most widely used is our urea and urea based fertilizers and diammonium phosphate and that kind of those kinds of fertilizers. So you can see how much CO2 we are contributing to the environment by way of consuming the fertilizer. Whatever fertilizer you are putting in the plant, to the plants, to the crops in the soil, maybe some of that is getting utilized by the plant for its growth. Rest all is going in water, right? So we are contributing in a huge way by simply by way of our fertilizer usage. So I wanted you to be aware that there is a huge footprint associated with any ammonia usage for any activity, whether it is fertilizer, whether it is amide based fibers, nylons or whatever. And we have got these calculations, we have got this number, we have got this number 1143. It is only based on the amount of air required to remove the oxygen from the air. You see where this CO2 is coming from. All the CO2 is coming from getting rid of this oxygen, isn't it? this oxygen has appeared. I wanted to get rid of this, therefore I had to introduce the partial oxidation, and therefore it is ending up as the carbon dioxide. Do you agree? Plus whatever the carbon monoxide we have generated by way of reforming, because we wanted the reformer to produce hydrogen. So we wanted CH4 plus water to give us carbon monoxide plus 3 hydrogen. This is what was required. Therefore, I had to make carbon monoxide, and to get rid of this carbon monoxide, I had to convert that into carbon dioxide. So this 1143 is only coming from raw material usage. What is the raw material that I have used? Air, methane, plus in addition,
Water.
and water. Yeah, obviously that oxygen also is coming from water, right? It is only coming from raw material. Plus I will have CO2 generated when I use electricity. When we are using electricity in this plant, for whatever reasons, maybe heating, maybe pumping something, so many places electricity we use. Every time we use electricity, it is coming from some thermal power plant by burning of coal or some fuel oil. We will generate carbon dioxide. This is something that we will see little later. How much CO2 is generated when we use electricity? This will come after mid-sem.
So I have one question.
Yes, yes.
So why can't we trade off price for a more green method?
Dry ice. Now, how are you going to get dry ice?
No. Sir, I'm saying why can't we trade off
Uh,
a greener method for the
uh,
price that we are paying?
which greener method?
So, like, if we consider any other method of separating nitrogen, which is more energy intensive but produces less CO2.
Right. So one way is, instead of using air, suppose this was our ammonia plant. So we don't use nitrogen, oxygen, we don't use air. Suppose I say that we take air, we do fractional distillation, separate out the oxygen, separate out the nitrogen, and then only nitrogen we feed, and therefore the partial oxidation we will not need, isn't it? But the carbon monoxide that is generated, that will still contribute. Do you agree, Arya?
So I'm like, even for the reforming, like we can use electrolysis of water on a large scale.
Good thing that you are talking about all this. So the point that we are discussing, we are not, look at it in a more philosophical way, we are not discussing just the ammonia synthesis. We are discussing what could be alternate routes. Oops, not routes, routes to make ammonia, which will be having lower carbon footprint. Is that what you are saying?
Yes, sir.
So, and in general, in a more generalized way, in a more philosophical way, we should be thinking about what could be alternate routes to make anything, any product, which will have lower carbon footprint. We are just taking ammonia as a case just because we are discussing material balance. But let's discuss now. Let's discuss two alternatives, right? Or maybe one alternative. What you are saying is we use this ammonia reactor. Okay, we make 1 ton of ammonia. Okay, how many kilomoles was that? Where did that go?
58.4.
Okay, 58.
58.8. Sorry.
58.28.
8282. Sorry. Not
58.82. All right. So don't worry whether it's 8 to 2, it doesn't matter. So we can say that ammonia we will make from nitrogen. Nitrogen will come from distillation of air, right? And oxygen will go away. Hydrogen, how much hydrogen did we want? 88.24.
88.24.
Right. So hydrogen we want is 88.24 kilomoles. This you are saying we will generate from electrolysis of water, right? So we will feed water, we will supply electricity, and we will get hydrogen from electrolysis of water. We will also get oxygen from electrolysis of water. Okay, so now our plant will look like this, right? Our plant will have, oops, I should draw air, right? Air. Okay, so now our plant will look like this. We will have water being supplied, we will have air being supplied, we will have electricity being supplied, we will have oxygen going out, and we will have ammonia going out. Isn't it? Is that what you're saying, Yash? Sorry, not Yash. Arya?
Yes, sir.
Just now, so we will not have CO2 footprint. That's what you are thinking. But what about the?
So we'll have a lesser footprint. Like whatever CO2 footprint we'll have will be in the energy that we are supplying. That is
Correct.
because of the energy that we are supplying.
All right. All right. Okay. Now, so let us say that. Okay. So one thing to worry about is how much extra electricity we will use. Okay. And what is the CO2 footprint of that electricity? That is one question. Second question is, what is the cost? What is the cost of raw materials? Isn't it?
Yes.
Now let's look at only these two alternatives, right? Let's look at, this is our alternative 2, and let's look at this as our alternative 1. Okay, let's not even worry about the electricity cost of let's not worry about the carbon footprint of electricity. That is anyway we are going to do in after our mid-sem, and this question we will be able to answer after mid-sem. Not that we can't do it now, it is just that something has to be done first, something has to be done later. So this question we will do after mid-sem. In general, not just electricity, in terms of heat, if I have to remove heat, if I have to supply heat, all that we will do after mid-sem. Let's only look at this second option just now. Okay, second part of the sustainability angle just now. So this was our first option. For every 1 ton of ammonia, we used 25.97 kilomoles of methane, and 25.97 multiplied by 16 is the molecular weight of methane. This is like 415.52 kgs of methane. All right. Is that okay?
Yes, sir.
Right. Now let's just not even worry about water. Assume that there is no water cost. Assume that there is no air cost. This is not what we are doing. We are supplying air. We are assuming that air is available plenty. Okay. So major raw material cost. So root 1, 1000 kilograms of ammonia requires 415 kilograms of methane, isn't it? And for root 2, we will say, air is free, water is free. So we will say practically zero raw material cost. Is that okay? Arya, I'm on your side.
Yes.
I'm
Yes,
on
sir.
your side. Not quite, but I'm on your side. At least as of now, it looks like. So what is the cost of methane?
So 50 rupees per kg CNG.
Okay, so CNG, let's say, is rupees 50 per kg. So what is the cost that I have incurred is 415 into 50. I have incurred 2077 rupees. Forget all that 77 and all that. Let us round off. 2100 rupees. Is that okay? All right. I have incurred 2100 rupees cost.
So 21,000.
21,000.
Oh, sorry. 415, 415 into 50. Sorry. 21,000. I have incurred 21,000 rupees of cost in making 1000 kilograms of ammonia. That means minimum selling price of ammonia should be 21,000 divided by 1000, isn't it? Are you agreeing with this?
Yes,
sir.
sir.
Okay. If I have anything below 21, I'm essentially losing money. If I sell it at 21, I'm basically having no profit, no loss. Just this is only a approximator. Don't take these numbers very, these are not very accurate numbers, because we have not yet worried about the cost of electricity. We have not yet worried about cost of water. We have not yet worried about cost of treatment of air. We have only said simplified thing that air is 7921. All that we have made so many assumptions, but this is the bare basic cost, isn't it?
Yes, sir.
Okay, now root 2. Say practically zero raw material cost. All right, practically zero raw material cost, but I need electricity cost. Okay, let's just quickly estimate how much electricity we will need. I have to generate by electrolysis 88.24 kilomoles of hydrogen. We need to generate not rupees, we need to generate 88 point, how much is that? 88.24 kilomoles. Oops, my handwriting should be proper. 88.24 kilomoles of hydrogen. So my electrolytic cell, I'm going to have water coming in I'm going to have hydrogen being generated. I'm going to have oxygen being generated. I'm going to supply electricity. Okay, if I have to generate 88.24 kilomoles of hydrogen, what is the reaction that is going to happen to hydrogen? That is one of the reaction that is going to happen at the, yes or no?
Yes,
Yes,
sir.
sir.
At the cathode or anode?
Cathode.
Cathode.
Cathode, right. Okay, so what is the voltage that I need? Anodic reaction also have to write. What is the voltage that I need? If I have to do this electrolysis, how much voltage do I need between cathode and anode?
1.2.
1.23 volts.
1.23 volts. Let's just say 1.5 volts. There will be some over voltage, some drop due to electrode, and all those things will be there. Let's just say 1.5 volts. We are just doing some rounding off,
Yes, sir.
some assumption.
Yes, sir.
Okay. How much current will be required, or how many joules will be required? Or maybe I should ask, how many coulombs will be required?
Uh, 172, 176.48 kilofarads.
170?
6.48 kilofarads.
How did you get that?
So 1 farad will be required to form 1 H. So for 1 H2 molecule, 2 farads will be required per mole.
Okay, and 1 farad is how much?
1 farad is equal to 9650 coulombs.
96,000?
97 or 98 for better measure.
98. Okay, let's take 98. Do you agree? Anybody agrees? Anybody disagrees? $96,500, right?
Yes, 96,500.
Yes, sir.
Do you agree with this? Do you agree with this? Do you agree with 176.5? Because we had 88.24, double of that, and double, and every farad is 96,500 coulombs. So total coulombs would be 96,500 into 176.5. Do you agree with this?
Yes, sir.
17 into 10 power 6.
What is the, how much joules are we using?
Into 1.5.
Into 1.5. So 17 into 1.5. 25.
26.
25.5.
26. Let's just round off. 26 joules. What is the cost of these many joules of electricity? 1 unit of electricity is 1 kilowatt hour. That is 3.6 into 10 raised to 6 joules. Do you agree with this? We saw this in the first lecture as well. when we were talking about units and conversion. Yes or no?
Yes, sir. Yes, sir.
Yes, sir.
So that means we are using 8 units of electricity to produce 88.24 kilomoles of hydrogen, or we should say we are using 8 units of electricity to produce 1000 kilograms of ammonia. Hey, wait a minute. Did we not multiply by 1000? 176.5 into 1000 did you do?
No, sir.
So this becomes 17 into 10 raised to 9. This is
26
kilomoles.
into 10 raised to 9.
Kilomoles.
Yes, sir. So 8,000 units of
So
electricity.
that means this will become 26 into 10 raised to 9. This would mean that we will have 8,000 units of electricity to produce 1000 kgs of ammonia. That means 8 units of electricity per kg of ammonia. Isn't it?
Yes, sir.
So now 8 units of electricity, what is the cost of that? In your house, how many units are you using? And what is the bill that you get? Anybody has seen their house electricity bill?
Sir, it's 8 rupees. 8.45.
So 0.2 rupees. 0.2
unit?
rupees per kilowatt hour.
Nahi re baba.
Sir, it's
I think it
8.45
is.
rupees.
So it is 6 rupees per unit.
Sir, it's 8.45 for 500 and above.
Yeah, so if you are using 500, it depends on how many units you are
Yeah,
using. And obviously in the plant, you are going to be using tons and
6
tons of,
rupees.
yeah, 6 is a basic number. And that is also because it's a domestic consumption. It's a single phase connection. Moment you have 3-phase connection, moment your number of units goes up. Let us just say on an average, shall we even say rupees 8 per unit?
Okay, sir.
Yes, sir.
Right? 6 is if your usage is below some number. If your usage is above that number, the rate changes. And obviously we are going to make tons and tons of ammonia. So therefore we are going to need large number of units. So we would not be in the lower bracket of electricity. We would be in the higher bracket of electricity. So even if you just say 8 rupees per unit, what is the cost?
48,000.
64 per kg,
64,000.
Yeah, sorry, 64.
right? So that means I should sell at least above 64 rupees a kilogram.
Yes, sir.
Yes, sir.
Now tell me.
So that's what I was saying, that for a lesser CO2 emission, you can trade off the price.
No.
Might be.
No. We have to still worry about what is the kgs of CO2 generated by this. Let me just tell you just some number. 1 unit, approximately, you will produce 1.3 kgs of CO2. This is some number. Don't worry about this number just now. We will calculate this number. Plus, efficiency of electrical conversion is about 30-40%. So 1 unit you generate about 1 kilogram of CO2. So that means 8,000 units means we will generate 8 kilograms of CO2 per kilogram of ammonia. how much we were generating?
1.1.
1.1. We were generating 1.1. We were able to sell at 21. If we use electrolysis, we will generate 64 rupees. We'll spend 64 rupees and we will generate 8 kilograms of CO2, which is more harmful to the environment.
Sir, but the first plant would also require electricity.
So that is anyway required. That anyway is required. So many pumps and all those things will be there. That anyway we will be having in this plant as well, isn't it? The cost of running these equipment, the electricity consumption in these equipment, that we have not yet considered. That we have not considered for this plant also. We have not considered for this plant also. Even without that, don't you agree?
Yes, sir.
Arya, what is your decision now?
So, but I still like we have other sources of electricity that will produce.
Like what? Like what?
So
Nuclear
what if we
power
use
or-
solar electricity?
No, Hardik, we'll talk about solar in a minute. Arya, which other source?
Nuclear power, we can use that to generate electricity, which
Okay,
would have a
now-
lower carbon footprint.
Okay. Now the debate is shifting to, we are not doing MEBC, we are just debating. Debate is now shifting to what is a greener method to generate electricity. I'm just saying greener. One, nuclear. So when we say greener now, we should not just think about greener in terms of carbon dioxide emission. Greener is one aspect of greener is CO2 emission. But nuclear, do you think it is greener? It has no CO2 emission, but what about nuclear fuel? What do you do with nuclear fuel?
So if we
What do
need
you
to
do?
dump it, you can't do anything of it.
Correct. So nuclear fuel, either generation and spent. Hydroelectric. Now you may say wind, solar, geothermal, what else? Wind we have talked, solar, geothermal, ocean, right? All these so-called renewable resources. What is the contribution? So just do Google. How much electricity India produces? And what is the percent contribution of nuclear? What is the percent contribution of hydroelectric? What is the percent contribution of wind? What is the percent contribution of solar? What is the contribution of thermal, geothermal, ocean? Or it could be thermal in the sense that coal, natural gas, whatever.
So nuclear is 3.22%.
No, that's okay. I mean, there's no, we don't want to look at numbers just now. I'm just saying that right now, what is the cost of this electricity? It is 8 rupees per unit because of what? It is based on some combination of all of these that government is charging 8 rupees. Isn't it? Government is having electricity from all these sources and it is charging customer 8 rupees. It is based on all these. Government is using all these in different proportions. Tomorrow, if the proportion changes, cost will change. Okay, but as of today, what is the contribution and what is the percentage? And that is the cost that we are getting. It is not that when we say 8 rupees, all this is included today. All this is included. Do you agree?
Yes, sir.
So I'm not telling that you are wrong. I'm only saying that as of today, this is the scenario. Tomorrow, if things are going to change because of maybe more nuclear, maybe more wind, maybe more solar, maybe more geothermal, this will reduce. And this will also reduce. Okay, but still there is a long way to go to 21 and 1.143. 8 has to become 1.1, 64 has to become 21. Only then farmer will buy fertilizer from you if you are using electricity for electrolysis. So if you are now talking about solar, so what we will have is we will have photovoltaic panels. And we will generate 8 units of electricity to make 1 kg of ammonia. Isn't it? So find out how much land is required. What is the cost of solar cells? What is the efficiency of conversion of solar to electric? That will decide your land. That will decide your cost of solar cells. So think about how much land is required. What is going to be the cost of that land? Versus what is going to be the cost of buying a land to set up this plant or this plant. Do you agree? I'm not saying answer 1 is better than answer 2 or option 1 is better than option 2. Yes, as of today, option 1 is a better option than option 2 for India. But that can change tomorrow. All I'm saying is what are the alternatives?
Sir,
1 second. All I'm saying is what are the alternative routes? What is the cost associated? What is the CO2 footprint associated? What is the land requirement? All these 3 taken into account will decide what is a viable route today. Okay, and there's no correct answer, there's no right answer. Route today may be better for today, another route may be better for tomorrow. All I'm saying is all these answers we can find for ourselves by material and energy balance. Okay, that's the whole message of this whole course, nothing else. We will do problems and we'll do this and we'll do that, and we'll have some continuous assessment tests and we'll have mid-sem and we'll have end-sem, but that is all meaningless. This is what we should be doing. This is what we want to learn in this course. That is the objective of the course, nothing else. Other things are all secondary. Yeah, somebody was saying something.
sir, I was saying that instead of changing the method, if we get any way to just use the CO2 which we have released, instead of releasing it in the atmosphere, we can use it for some other purpose.
Like what? Tell me.
Like sir, I have seen like ICT also there is some research going on algae, like
Well,
we can use
CO2 will
algae for
utilize for
CO2.
what? CO2 to algae?
Yes, sir. Algae needs CO2 for its production, and we can sell algae-based products like
So
if you need.
CO2 to algae. What we'll do with algae?
So we can
Make fuel out
treat
of
it.
it, or make food additives out of it,
Yes, sir.
or make pharmaceutical products out of it. Right? So many things we can think about. Right? Just
Yes, sir.
look at Google is there at your fingertips, right? Just look at what is the worldwide production. What is the worldwide production of ammonia? How many tons are produced per year? Correspondingly, you will know how many CO2 is produced in terms of tons per year. Now, what is the combined market of all of these? You find out for yourself. Okay, there's one more route that we can take. That brings us to our next problem.
So we
Yeah,
can form ammonium carbonate, and from that we can make urea
yeah.
by using
Anyway,
the CO2.
correct. Anyway, the urea that is made from ammonia and carbon dioxide. Anyway, the urea that is made is by utilizing the CO2 here. So this CO2 plus this ammonia is what goes into urea production. So already it is being used, right? But what is the urea production? Sorry, what is the urea? I have 2 moles of ammonia plus 1 mole of CO2 is giving me urea, isn't it? So 34 kgs of ammonia will react with 44 kgs of CO2, isn't it? So already when you make urea, already a lot of this CO2 is utilized. Already a lot of this CO2 is utilized. We are making 1.14, right? 1.14 kgs per ton of per kg of ammonia. So already it is favorable to make it urea. This is already there. 44 by 34 is already 1.33 approximately. 1.3. So already we are consuming all the ammonia, all the CO2 produced. So yes, this is very much favorable. Now we have to only worry about how much CO2 is generated by way of electricity, use of electricity, right? So if I do this, definitely I will not be able to utilize all the 8 kgs, whereas I am able to utilize all the CO2 that is generated here to make the urea, because I'm making so less carbon dioxide. That's why I need a purification system. Okay, there is yet another way in which we can utilize the CO2, is something called as dry reforming. So rather than using methane and water for doing reforming, we will do methane plus CO2 in the reformer and generate carbon monoxide and hydrogen. So the reaction would be CH4 in the gas plus CO2 in the gas phase. It's a high temperature reaction. It's an equilibrium reaction. CO plus hydrogen, right? We will have 2 hydrogens that are coming. Okay. Can we go to this problem? Want a break, or we can go to the problem? I can describe the problem, and those who want to have a break can have a break. Is that okay?
Yes, sir.
Okay, sir.
Okay. So we need to now think about equilibrium kind of reactions. So this is one problem just to give you that. Oh, obviously I will need 2CO. You should stop me and don't allow me to go forward unless I balance the reaction. Okay, so the equilibrium constant Kp is 0.19 atmosphere square at 873 Kelvin. Equilibrium constant Kp is 1.31 atmosphere square at 923 Kelvin. Okay. So let's say that reformer, this is operating at, let's say, 923 Kelvin, 1 atmosphere absolute pressure. So temperature is 923, total pressure is 1 atmosphere absolute. Mole ratio of methane to CO2 is 5:1. Calculate one equilibrium conversion of methane and CO2. So we are assuming that equilibrium is reached in the reformer and the gases are come out are at equilibrium. So obviously if I'm having equilibrium, what will come out of the reformer, and mole ratio we are having 5:1, we will have unreacted methane coming out, we will have carbon dioxide also coming out. So this will be, these four coming out will be at equilibrium. We are assuming that equilibrium is reached in the reforming reactor. Okay. Second, okay, let's just do this one first problem just now. Solve. Fairly straightforward problem.
Sir, could you please show the whole question again?
Yeah. Okay, now people want to have a break, can have a break. You can continue solving.
So we have to say the percentage composition.
Yeah, percentage conversion.
Percentage conversion. Uh,
Of methane as well as carbon dioxide.
1 minute.
Yeah, sure. Take your time.
Sir, can we consider the dissociation as small?
Can we consider what as small?
The dissociation constant as small.
Dissociation constant for what?
Sir, the in the equilibrium the amount is subtracted. So can we consider it small? Then the equation to solve becomes easier.
So
How can you make that statement? There's no dissociation. Methane is reacting with carbon dioxide. I'm not understanding what you're saying by dissociation of what. Are you saying methane
Man, sir,
dissociates into
sir, there is an
CH3 minus and H
equilibrium.
plus? No, what are you saying? Dissociation of what?
Sir, sir, it's not dissociation constant. It's
Huh.
actually a relative term, an analogous term.
So
Sir,
what are
wait,
you
I just
asking?
check.
No, what are you asking? I'm not clear what you're asking.
Sir, just check it 1 minute.
And you can check, but I'm not understood what you're asking. Methane is reacting with carbon dioxide to give us carbon monoxide and hydrogen. Equilibrium constant Kp values are given at two temperatures. I'm telling you reactor operates at 923 Kelvin. So obviously this is the relevant value of Kp to use. And we are saying it is at isothermal if you want, or at least whatever gas comes out is at 923 Kelvin and 1 atmosphere pressure and is at equilibrium.
So conversion for methane is 12%, and conversion for CO2 is 61%.
All right, that is one answer.
Yes, sir. 12.2 and 61.1.
Sir,
Suppose
Yeah, go ahead.
so we are getting CH4 as 19.18% and CO2 as 95.9.
yes, sir. 19.18 and 95.9, sir.
Okay. We'll just wait for some more people to answer. Anybody stuck? Anybody wants hints?
Yes, sir, it is 12% and 61%.
Okay, 12 and 61. Any other answer? No other answer? Only 5 people have solved so far?
1 minute, sir. I guess there is a correction I have to make.
Okay. Anybody stuck? Anybody wants hints to solve?
Hello, sir.
Yeah.
Sir, I'm getting methane as 16.4% and CO2 conversion as 82.3.
16.4, 82.3. Okay. Anybody wants hints? Nobody wants hints also. Nobody's telling me answers also. Any other answer? Anybody solving? Nobody's solving, looks like.
Yes, sir.
Yes, sir.
Solving. Oh, okay. Should we see the solution? Do you need more time?
Sir, 2 minutes, sir.
Okay, okay, okay. Remember all our steps that we have done. Select a basis. Write all the compositions, quantities in the form of tables. Think about control volume. Do material balance. What comes in minus what reacts must be equal to what is going out. For reactants, what comes in plus what is generated must be equal to what is going out. For products, atom balances. So there's no reaction for atoms. Total mass must be satisfied. Total mass must be conserved. Total mass coming in must be equal to total mass going out.
So I'd change my answer to 95.9 and 19.2.
Earlier you had given 12, right?
Yes, sir.
And 61. So I have removed from there and put it here. So 6 people have solved so far. Anybody has tried all those practice problems that are there on the Google Classroom?
Yes, sir.
Yes, sir.
Good way to spend weekend doing those? Or one weekend is not enough? Perhaps we need more weekends.
So more weekends.
So take as many weekends as you want. There will be some more problems that will be shared as we go along. Only 6 answers so far. Other people are doing, not doing. Shall we quickly see the solution and then you can solve afterwards?
Yes, sir. Yes, sir.
So this is an equilibrium kind of reaction. So if I say, let's say basis, all right, if I say basis as let's say 5 gram moles of methane coming in and therefore 1 gram mole of CO2 coming in. That's the mole ratio that we are supplying to the reactor. So if I say in terms of gram moles, 5 gram moles of methane and 1 gram mole of carbon dioxide that is supplied to the reformer reactor. Now equilibrium is going to be established. That means I'm going to have methane also coming out. Carbon dioxide also is going to come out. CO is going to come out and hydrogen is going to come out, right? So if I say out of this 1 mole of CO2, suppose I assume that X gram moles of CO2 react. If X gram moles of CO2 react, I would have 1 minus X gram moles coming out of the reactor. And our stoichiometry is 1 mole of methane reacts with 1 mole of carbon dioxide. That means X moles of methane would also have reacted. So what comes out of the reactor, methane that comes out of the reactor would be 5 gram moles that we supplied minus X gram moles that we react. Carbon monoxide, 2 times is the stoichiometry, 2 times the number of moles of methane or carbon dioxide that react. So carbon monoxide coming out would be 2x. Same way hydrogen coming out would be 2x. Right? So far, okay. Now, I'm told Kp, right? So we are told Kp. What does Kp mean?
Yes, sir.
It is the equilibrium constant for the reaction. How do we define this Kp? Kp in this mixture that is at equilibrium In this mixture that is at equilibrium, Kp would mean partial pressure of CO square, partial pressure of hydrogen square divided by partial pressure of carbon dioxide and partial pressure of methane. Do we agree with this?
Yes, sir.
Now partial pressure, how can we write partial pressure? It would be mole fraction of CO multiplied by total pressure. That would be partial pressure of carbon monoxide. So the numerator would be partial mole fraction of CO multiplied by total pressure square. That is the first term. Second term, partial pressure of hydrogen. That would be mole fraction of hydrogen multiplied by total pressure. That would be square. In the denominator now, in the denominator, I have partial pressure of carbon dioxide, that is mole fraction of carbon dioxide multiplied by total pressure, and partial pressure of methane, that will be mole fraction of methane multiplied by total pressure. So if I can cancel out the total pressure from here, total pressure from here, and total pressure 1, I can cancel out because anyway it is square. So this Kp I can also write as mole fraction of CO square, mole fraction of hydrogen square, total pressure square divided by mole fraction of CO2 and mole fraction of methane. So all I have to do is convert these gram moles into mole fraction. How do I do that? I can do that if I know the total gram moles that are coming out. What is the total gram moles coming out? 5 minus x plus 1 minus x plus 2x plus 2x. So this would be 6 plus 2x total. Mole fractions would be 5 minus x divided by 6 plus 2x. 1 minus x divided by 6 plus 2x. 2x divided by 6 plus 2x. 2x divided by 6 plus 2x. Right? So all I have to do is now substitute the values. So Kp is 1.31 atmosphere square and total pressure I have told you is 1 atmosphere. So we can write from here now. Isn't it? Mole fraction, I'm just writing it again, mole fraction of CO square, mole fraction of hydrogen square divided by mole fraction of CO2 and mole fraction of methane multiplied by total pressure square. This is 1.31 and total pressure is 1 atmosphere. This also is in terms of atmosphere. So I can just 1 square is just 1. So now mole fraction of CO that is coming out. This is nothing but 2x divided by 6 plus 2x the whole square. Same way hydrogen, mole fraction of hydrogen coming out. 2x divided by 6 plus 2x the whole square. Mole fraction of carbon dioxide. 1 minus x divided by 6 plus 2x. Methane. 5 minus x divided by 6 plus 2x. Right? So now I can simplify 2x square, that will give me 4x square, another 4x square, denominator 1 minus x, 5 minus x, and then 1 of the 6 plus 2x I can cancel from the numerator on, sorry, 1 of the 6 plus 2x I can cancel. So this denominator I can cancel with 1 of that because anyway it is square outside. And then this would be additional term that would be there, would be 6 plus 2x the whole square. This would be equal to 1.31. Do you agree with this?
Yes, sir.
Yes, sir.
Now how do you solve?
Yes, sir.
First semester, you have done some methods of solving nonlinear algebraic equations. That's why the maths course is there. Have you solved nonlinear algebraic equations anytime? Maybe 12th standard you have solved. Which method do you know of? You don't know any method of solving nonlinear algebraic equations? Don't you know any method of solving nonlinear algebraic equations? Nobody knows any method. How is that possible? Are you able to hear me? Am I audible? Is anybody around?
Yes, sir. Yes, sir.
Yes,
Yes,
sir.
I was wondering if nobody's around, that means connection is gone. Nobody's answering anything. Any method that we know of nonlinear algebraic equations, solving nonlinear algebraic equations? Surely, 2-3 methods you will be able to tell me.
So a regular Falchi method, Newton-Raphson method.
Ah, second one?
Regular Se- Falchi method. secant method.
Secant method, okay. This one? Name rings a bell. I, and so many dashes. E.
So regular Falsi.
Does it look like this second one?
Seidel.
Seidel.
Iteration.
I'm sure you've heard of this. The number of dashes equal to one letter each, right? You never played this game?
Sir, hit and trial.
I mean, does it look like I'm spelling out hit and trial?
No, sir, sir.
No, okay. So I'm trying to
Bisection.
spell out. Gauri is wide awake. You must have played this game earlier, Gauri. So
Hangman is the game.
yeah, Hangman is the game, I know. And if you don't do it in 5, the man gets hanged. All right, but anyway, your calculators, that's besides the calculators can solve nonlinear algebraic equations. Download manual of your calculator. If your calculator is FX 991 something 991 ES or ES plus, these can solve nonlinear algebraic equations. Even other models can solve nonlinear. So if you just program this in your calculator and just say solve, it will tell you the value of X. And in this particular case, X that is right is this. Oh, answer is gone. But 95.9% conversion of CO2 and the corresponding conversion of methane, whatever that value is. Okay. Second thing I want you to do is the reason why I am giving you this expression. The reason that I have given you values of Kp at 2 temperatures at 873 Kelvin and 923 Kelvin. I want you to find out at what temperature our conversion of CO2 would be 99%. Okay, so this you can do as homework. So obviously temperature is unknown, but I have given you Kp values at 2 temperatures, right? So I will tell you, fit an expression for Kp, 2 values of Kp, 2 values of corresponding temperature. You can fit a linear, but I don't want you to fit a linear. I want you to fit an expression of this type. Ln Kp is equal to A plus B by T. This kind of expression, if you fit, so find constants A and B. Once you find constants, you will know how Kp varies with temperature, and you can extrapolate to any temperature. And I want you to find out the temperature at which conversion would be 99%. Okay, so I want you to do this problem. We will stop here for the day. Just some instructions, don't log out. Just some instructions. What about your afternoon lecture? Any inputs on that?
Not yet, sir.
Okay, so anyway, we will assume that lecture is there. So anyway, what time your lecture was supposed to be there? Lecture was supposed to
2:30 to 3:30.
2:30 to 3:30, right? Yeah, when will you tell me, or how will you be able to tell me?
Sir, till 2:30, if no reply comes, then that would be obvious.
So lecture is not there. Anyway, it doesn't matter. Anyway, if 2:30 to 3:30 lecture is there, or 2:30 to 3:30, or 3 for 30 gets extended to 4 o'clock or whatever, we will have a quiz from 5 to 6.
Okay, sir.
Okay, and let's not worry too much about this 6. Let's make it 6:30. All right. So quiz will come to you at 5 o'clock, and then you will have to turn in the answers by 6:30. It will be same as last time, meaning the methodology will be same as last time. Questions obviously will be different. Okay, but the same way. Okay, so solve honestly. That is in your best interest to solve it honestly. Don't worry about the grades. Don't worry about the continuous assessment marks. We will have enough number of continuous assessment tests, and we will take such a less number of continuous assessment tests out of the total that we conduct that nobody will suffer. Nobody will suffer because one of the quizzes was bad. Doesn't matter. You will get plenty of opportunity. So no cheating, no copying. Solve it honestly. It is for your own benefit. Okay, so quiz will come at 5 o'clock. You have to turn in by 6:30. Okay, shall we stop for the day? Let's.
Sir, I wanted to ask something.
Yes, sure. Go ahead.
Later,